Hello, my name is Matt, and today I'm going to be teaching you how to derive all the maths behind the gradient descent algorithm for linear regression. Just before we start, I want to say that this video is going to be part of a post about implementing gradient descent for linear regression in Python using NumPy and Pandas. So if you're interested, please check out the link in the description. It will help me out quite a lot. Firstly, I want to say a few words about what gradient descent actually is and the motivations behind it. As you may know by now, gradient descent is a very popular algorithm in the fields of machine learning and data analysis. The purpose of gradient descent in the context of linear regression is to find a line that fits your data in the best way, so that you can make predictions, extrapolate, or interpolate the data. So for example, in this fictional data set that I've got here showing you, it's just a data set with one variable and one outcome, which is the y-axis here. We can perhaps say that this data set represents the value of houses in a particular area of your country. So the x-axis could be something like the area of the house, and the y-axis is the actual price of the house. Okay, so as you can see here, you can almost fit a perfect line here that goes right through your data, so that if anyone asks you something like, what does a house cost if the area is around somewhere like there? So with gradient descent, once you find this line, you can then make predictions by just putting your input value here, your x, your area in this particular case, and seeing what the outcome would be. And this is based on your input samples that you had in your data set. Now, gradient descent achieves this by minimizing what we call a cost function. You'll see what this means in a bit. But basically, a cost function is some sort of measure to say how good a line fitting actually is for your particular data set. For example, we fitted this red line here, which seems to fit quite well in the data set. But we could have as well have added a line here, and the predictions wouldn't be so good because basically for every point that we have, the actual prediction is way off compared to the data sets that we actually have here. Okay, so likewise we could have had a line around here, and the cost function would be very high. In other words, the error would be very high. Or we can have a line that doesn't can go through the data but doesn't quite have the right slope for it. So somewhere like that. For most cases, the distance between the actual prediction that your line makes compared to your samples in your data set, the actual values, they would be quite high. Therefore, the cost function would be a high cost as well. So this is what gradient descent does. We define a cost function for a particular prediction, and gradient descent minimizes that cost function, finding the right fit for the data set. In other words, it will find the perfect line by minimizing the cost function and finding all the values that would represent a line here. Okay, so let's actually get started. So what is the problem that gradient descent in the context of linear regression here is trying to solve? So basically what we want to find is that for any given input vector that we have, so for any given input sample, we want to make a prediction of what the data set actually is. In other words, what the data point would actually look like in a data set with a linear function. So what does that look like in terms of maths? That basically looks like something like this, We've got a constant term here, and for every component inside the input sample, we've got a weight times that component. So in other words, what am I saying? I'm saying that, for an input vector x that kind of looks like this, f of that x tilde is going to make a prediction. It's going to output one value that is a linear combination of all the components inside the vector x here. Okay. Now to make this a little bit simpler, we're going to write this function in terms of vectors. Okay, so we're going to vectorize. I'm not sure if that's a word. We're going to vectorize this function. So the first thing I'm going to do is I'm going to basically ask you to forget a definition of a data sample here for a second. And what we're going to do is for every data sample that you have for the x, we're going to add one additional dimension at the start, and that is always going to be a 1 at the start. And you'll see why I'm doing that just in a second. So in other words, your x is now going to look like this. And this now is an n plus 1 by 1 column vector, okay? And we're also going to define a vector of weights, w tilde, which contains all the weights that we have in our function here. So, starting from w0, and these are the coefficients of our components in the input vectors, basically. So the reason why I've added an extra component here with the input samples is so that we can write this function now, f of x tilde, as simply a dot product between w and x, and that would look something like this. I'm sure you understand what a dot product is, but if you times each component by the equivalent one in the other vector, you're going to get 1 times w1, which is w1, plus w1 times x1, w2 times x2, and so on. So basically we just rewrote the function in terms of vectors, okay, which might help us in the future, as this problem is essentially a matrix and vector multiplication problem. But we've not actually got to the gradient descent bit yet. We just basically stated what we actually want to do with gradient descent, which is to find, you know, a set of weights here which represents the line, such that, you know, if you do your dot product of your input sample with the weight, that is essentially going to be your prediction here, or your red line. So how do we do that? How do we actually do this? Well, if you remember well, I said that gradient descent works by minimizing a cost function. So I tried to explain a little bit what a cost function is, but it's essentially the measure of how good your line actually is compared to the actual samples in your data set. So for the context of linear regression here, the cost function, we're going to define it as the distance between your actual prediction and your points for each data sample. That distance is going to be squared, and we're going to sum all the distances between the predictions and your data samples in the data set. Okay, so what do I mean with that? Basically, our cost function is going to look something like this, you know. In this particular variable yi here means the actual output of the data set. Okay, so if our data set looked something like this, and if it's a one-dimensional problem, for this particular point here, you know, this will be the x value, so the actual x vector, which would just be a one-dimensional vector, and this would be our, you know, our yi here. I don't know which particular point this is. It might be the 10th point, I don't know, but we just, you know, this is the output, and that is the vector. Hopefully that helps you visualize things a little bit better. So now let's bring some definitions into this. Okay, so basically we've defined our cost function here, which actually, you know, if we expand it a little bit more, equals something like this. Here I'm using x superscript I to represent the I data sample in a data set. Okay, so our cost function looks something like this. But now let's also vectorize and bring in matrices into the equation. Okay, so let me make one definition before we go any further. So let's define the vector y tilde as the column vector of all outcomes of our data set. Okay, so it will look something like this. And it's worth noting that I'm assuming that we have m data samples and m outcomes in our data set. Okay, so basically this vector here is an m by 1 column vector. Okay, and let's also define a matrix x, big X, I'm using, you know, a capital letter to denote matrices, where each row of this matrix is the corresponding data sample in our data set. Okay, so in other words, each row is the data sample corresponding to the row in our data set. Okay, and these have obviously the first data sample has to match the first outcome, and the second one has to match the second outcome, and so on. Okay, I can even expand this matrix so you can see what it looks like. I might fast forward this. Okay, so I've expanded the matrix here, and you can see that on the first row, this is essentially all the components of the first data sample. And I've kept the superscript to represent the number of the sample that it is. So this is, you know, the first row is the first sample in a data set, and the number on the bottom here represents which component it is. So we start with the 0 component, and we have the first component or the first feature in the vector, and the second feature in the vector up to the nth one. And it's worth noting that in our particular case as well, this first column is all going to be, you know, full of ones, because we've defined all the first dimensions to be equals to 1, as we, you know, explained previously here. So this is the definition of our X matrix. Now, going back to the cost function, we're also going to vectorize and sort of turn this formula into a matrix multiplication problem, okay? Because we'll make things easier in the future, and you'll see why. Now, let's consider one particular multiplication. Let's consider this multiplication here. So x times w here. So as you know, matrix multiplication works by taking each row of the matrix on the left-hand side and timesing it by each column of the matrix on the right-hand side. So in this particular case, we have x is actually constructed by taking each sample and spamming the rows there. So we've got x1 as the first row, and then you've got x2 as the second row, and so on. We're assuming that we have m samples, so it goes up to xm. Okay, and this is the matrix itself. And if you want to sort of visualize what it actually looks like, you can look at this bit here at the start, because we've actually written it out. And this is going to be times by the w. And this obviously works because this matrix, as we know, this is we can see here, is an m by n plus 1 matrix, okay? Because we have m data samples, and each data sample has n plus 1 dimensions because we added, the 1 here. And this is an n plus 1 by 1 column vector, okay? So what this actually looks like, well, you actually get an m. We're expecting to get an m by 1 column vector here, and the actual result is the following. Well, we're going to take the first row first of all and times it by the whole the whole vector here. So this is essentially, if you can see what I mean here, this is w transpose times x1, okay? And this is our first component here in the column vector. And the second one is going to be the exact same thing, but with the second data sample. So you're going to get w transpose x2. And again, if you want to actually see why this is the case, you can write the matrix out and multiply things yourself. But this is what you're going to get. And I'm assuming that you're fairly well versed with matrix and vector multiplication, so that you can just see this result straight away. And this is obviously going to go all the way down to w transpose x to the m, xm transpose, okay? Which is interesting. Now, if I consider this particular multiplication, this particular vector addition or subtraction here, we get something that's very interesting indeed. Obviously, we're going to get this y minus this result here, and y has the same dimensions as the result of this multiplication here. So we can just do component wise as you'd expect. So it'll be sort of y1 minus w transpose times x1, and then y2 here minus w transpose. My tildes are looking a bit off, and I'm sorry about that. x2 all the way down to ym, so the m output minus the m prediction, okay? Which kind of looks like this. And if I can draw my lines correctly, there you go. Okay, and now this is something I'm actually going to show you guys later. And now for the icing on the cake, shall we say, we know that this vector multiplication addition equals to this, right? So if we simply do this value that we've just considered here, transposed, in other words, transposed and times by itself, what do you get? Well, you get the cost function of a particular w, okay? And why is that? Well, that's because when you take a vector and dot product with itself, you get the sum of all the components squared, okay? So you know the components of this addition and this vector multiplication here. And if you look at the cost function up here, you can see that this bit here is the same as, this bit here, for example, if you just consider I equals 1. And because of the sum here, we're summing all of these up, and there should actually be a square here, I just forgot. So, the dot product of this with itself would be each of these components squared plus, adding the other components as well. In other words, we get exactly the cost function. Now, I understand that we spend perhaps quite a bit of time trying to rewrite the cost function in a sort of vector/matrix form, but this is all going to be very useful for us when it comes to actually deriving the gradient descent rule, which we'll get to in just a few minutes. And you'll see clearly why it will help. But anyway, before I actually get into the derivation of the gradient descent rule, I just want to say a few words about a little bit more about where it comes from. So this is, perhaps a random sort of curve. This is actually, an x squared curve. I think I plotted on Wolfram alpha. Okay, and this is, I understand this is just a one-dimensional problem. But what gradient descent actually does is the following, right? So for a given curve of the cost function, okay, this represents the cost function. I'm not sure if I said that. We have a particular surface or a line in this case, and what we're actually going to attempt to do, or what we're actually going to do, is to get the gradient vector of that line or of that surface, and that gradient vector basically tells us, for example, it will tell us the direction of where the curve is going at a particular point in the surface. So in this particular case, is just a derivative problem. For the one-dimensional case, it tells us, as you know, dy over dx tells us how much change in y you have for a unit of x that you move, towards the positive axis there. But if you can picture this as a multi-dimensional problem, that gradient vector tells us the direction of where the curve is going at a particular point on the surface. Okay, so in other words, if you move sort of one unit in each dimension, how much change do you get in the cost function? Okay, and this could be positive, this could be negative. But basically what we do with this information here, once we have the gradient vector, we essentially do little iterations where we take away a fraction of the gradient vector from the w's. Okay, so instead of walking in that direction, we're going to be walking our w's in the opposite direction in a much more controlled way. In particular, is usually the fraction is a lot less than 1. So for each iteration, we're going to be walking down the curve. I'm not sure if you can see it. It's going to get so small that we're going to reach, here. The cost function will be very low. And this is a local minima of that particular function. Now, because we're talking about linear regression here, and the cost function is essentially a square function, I think it's always, if I'm not mistaken, it's always going to find the absolute minimum, or it's going to get very close to the absolute minimum. In other words, where the difference between your predictions and the actual outputs are sort of close to the absolute minimum that it could be. Okay, it won't be 0, because I'm sure you can understand, this particular data set here represents that. You can't have a line that goes through every point in your data set, but you'll be, very close to the absolute minimum. And that's what gradient descent is going to find us. So what we're trying to find here, what I'm trying to say with all of this, is that we're essentially going to be looking for the gradient vector, and I think it's represented in maths like this, of the cost function with respect to each component, to each w. Okay, and this gradient vector essentially, is defined as a column vector with all the partial derivatives. And I'm hoping that you know already what this means, and I'm assuming that you do anyway. So, it's a vector with all the partial derivatives of c with respect to all the components. So this is what we're trying to find with gradient descent, and this is what we're going to be calculating in the algorithm to help us reduce the cost for every iteration, as I showed you before here. Now, to make this problem a little bit easier to solve, we're only going to consider a particular partial derivative, for example, the first one. Okay, so let's consider, the partial derivative of the cost function with respect. I'm sorry about the partial derivative sign. I know it looks like a 2, but it's the partial derivative sign, I promise you. So let's consider the partial derivative of c with respect to a wi. Obviously, the I is an integer, between, 0 and n, because we have n plus 1 different components in w. So that partial derivative is essentially, the partial derivative with respect to wi of our cost function. And if we just rewrite the cost function here in its sort of non-vectorized form, because I think it's a little bit easier in this particular case. So this is our partial derivative. Now, let's just expand this a little bit more to make things simpler for us and for you to actually see what the pattern is here. Okay. And to make things even simpler, I mean, I'm sure you can tell there's, every term is basically the same. And as you know, the partial derivative of a sum of terms is equals to the partial derivatives of each term, summed up. So we can just consider, what happens when you take the partial derivative with respect to wi. of, let's say, one of these terms. Let's call it, let's keep it general again. So, wk minus, sorry, yk minus w transpose x to the k. In other words, the k difference squared. Because all of the same, I'm sure you can understand, all of the terms will have the same partial derivative. So if we can find what it is for this particular general term, we can just plug it back in and we find the final answer. Okay, so for this problem, we're going to be using the chain rule, okay? And we're going to be basically substituting this whole bit inside the brackets as u. And as you probably know, if we call this whole thing here, let me actually make use of this now. If we call this whole formula inside the bracket here, including the squared, as, I don't know, g of w, okay, then, the partial derivative of g with respect to a wi is equals to the partial derivative of g with respect to u times the partial derivative of u with respect to wi. This is something I expect you to already know about if you've done any maths, and it's what we're going to use to find this particular derivative here. So g of w is essentially, if we substitute this whole thing as u inside the brackets, we get u squared. In other words, u is equals to this bit inside the brackets. I'm not sure if I made that clear enough, but it doesn't hurt to write it again. Okay, and so let's find each term. What is, difference of partial derivative of g with respect to u? Well, that's fairly easy in this case. It's simply 2u, okay? And the partial derivative of u with respect to wi, well, this is, a little bit more tricky because we probably need to expand this bit inside the brackets. So u, as we know, let's write it up here. U is equals to yk, and then if we expand the vector multiplication out, we actually get, what we had at the very start as a definition of our prediction line, which is w0 plus w1. So, as you may know, when you take a partial derivative with respect to a variable, you basically just care about the terms that have that variable in it. In other words, we care about the terms with wi in it because the rest of them are just constants and they differentiate to 0. Okay, so the only time you're going to see wi here is in the term here in the middle, where you're going to have wi times xki. Okay? In other words, this will differentiate, everything else is going to differentiate to 0 in the first place, but this here is going to differentiate to simply, wi goes away because it's to the power of 1, and it's simply going to be ik here, okay? Before we forget as well, we did have a minus here with this whole bracket, so this term would actually be a minus term, in which case this will be a minus xki, okay? So now if you put 2 and 2 together, we have that the partial derivative, as we had here, of this whole thing here. Let me just write it again for us to see. That is equals to this here times this here. In other words, if I just simplify things a little bit more as I go along, we have minus 2 x k, and then we've got I here at the bottom, and then times u we would have here, but if we actually plug back what we had in the first place, u is equals to the bit inside. So what do we have there? We have the whole partial derivative is simply equals to this. And this has actually made, the problem fairly obvious now, because we found the partial derivative of one of the terms of the original thing we were trying to find the partial derivative of, which is this here. We found one of those, basically. But all of them are the same, because as you can see, the problem is exactly, the terms are exactly the same. The only thing that changes is the number of the sample that we have here, and obviously the outcome as well, the y value. So in other words, we can now write the partial derivative of c with respect to wi We need to be careful here with the variables because I'm aware we reused some of those. But basically this is, you know, the sum of -2 and xi here. And before I continue, I'm just going to put my variable here. We were summing over, I think, the samples, right? So let's use a j now. So j equals to 1 and it goes up to m. And obviously the sample itself will be j here. So the x superscript j and the ith component, and that's going to be times by ij minus w transposed xj here. Okay, so basically I substituted the k here for the j in here. So let's take a step even further now. Let's transform this into, again, a vector slash matrix multiplication slash addition form, because it's going to make things a lot simpler to write down as well. So let me just add a new page. And starting with that definition that we had here, let's put this into a vector form. And the way we do this is simply by, you know, if you look at the sum here, we can take the 2l in the first place, you know, the -2l, and we can create a vector with all these terms here, and you see what I'm doing in a bit, all the way down to xmi. And if we transpose this and times it by the bit in here, what do we get? We've got this, we've got the dot product of this vector times this vector, which gives us exactly this sum here. You know, you can times it out if you want, or you can just see it straight away, hopefully. And you know, this is this component times that component times the -2, and you get the first, you know, the first term of the sum. And then if you do the second one as well, this times that times the -2, and you'd also get the second term of the sum. In other words, when j is equals to 2, and so on. Okay, but let's just note one thing here. Remember when I said that turning all of the cost function and the formulas that we had previously into a vector form would help us. What is this here? Do we recognize this? Well, if I take you up to just about here, you know, this is what we have there. You know, this is the exact same vector that we have down there. And this vector is just equals to this, right? So if we replace that, you know, now we have all of the same thing, but in fact we can turn this into an even better equation by putting it into the matrix slash vector form. Basically, we simplify this quite a bit, and going even further than this, if you think about this particular term here, what is this term? Well, you see, I've got the first input sample, and I've got the ith component of that, and I've got the second input sample, and I've got the ith component of that, and so on, up to the mth sample that I've got, and then I'm taking the ith component of that, in other words, the ith column of each row in our vector of input samples. Let me just bring you up here if it hasn't been exactly that clear yet. So when we had x here, what we're doing in that particular case down there, we are taking a particular column. We don't know what column it is. I'm just taking it k equals, or the I equals 1 here for you guys to see. This is what we're doing. This is the vector that we have down here if I was equals to 1. Okay. So I'm going to use a little bit of a weird notation, which people may not have seen in maths before, if you haven't done any Python in particular before. So this is equals to, if you just bear with me, and I'll explain what this means. So this particular notation is a bit interesting because, you know, if you've done Python before, you know what it means. But in this particular notation, what I mean is from the matrix X, I'm going to take all the rows, in particularly all the values in the ith column for all the rows. In other words, I'm basically representing this here. You know, if this particular column would be, in that case, X, you know, all of the rows, but I want the first column here. Okay, this is what it means. This is what I mean by that. Okay, so now we have a much easier way to write this particular partial derivative. And because we've done this in a general way, we can actually construct that gradient vector that I was talking about, the so wanted gradient vector for gradient descent. So let's do that. So we've got the initial problem that we want to gradient descent. So the initial problem that we want to solve with gradient descent is to find the gradient vector of the cost function. Okay, and for that, you've seen that this is basically defined as a column vector with all the partial derivatives in each component, starting from W0 to Wn. And now we have a way of doing that. So basically, this would be, if I simplify as I go along, if I take the -2 out, we have x, all the values in the 0th column. In this particular case, I know that usually I start with 1, but 0, simply because we have a column of x here where all the values are 0. So let's call this one column here 0, and this one column 1. I think I already did that. I'm not sure if I explained it before. Okay, and so on. So instead of starting from 0, we're going to start starting from the first column. We're going to start from the 0th column. So we've got that times y minus xw, and the same thing for the other one, for the first column. So we're going to take the first column, and the same thing here, and so on. So this is our gradient vector. Okay, we can do even more simplifications with this though, and this is sort of the icing, the final icing on the cake, and I promise you guys it won't take any longer. So we can leave this vector as it is here. So what I've done here is that I have again split this equation here into a multiplication of a matrix and a vector. And this particular matrix is interesting because I am taking essentially the 0th column here of x and turning it into the row, and doing the same for the first column, or the second column if you're starting from 1, and turning that into a row of this new matrix, and so on up to the last column. And then I'm timesing that by this side here, and this is mathematically equivalent to this equation here. But what's even more interesting is that if we look at this is essentially the first column of x as a row, and then the second column of big X as a row, up to the last column of x as a row. And what is that equals to? Well, if you've guessed it right, that is equals to simply x transpose, and then you can do this here. So this is our gradient vector. This is exactly what you see in websites where they teach you how to implement gradient descent, and this is what they say, you can just do this multiplication to find the gradient vector for linear regression, and you get your result. So we've gone through all the maths that basically derives this tiny little equation here, which is the heart of gradient descent. Okay, and as a post-recording note, I just want to say that we acquired this formula down here for the gradient vector of the cost function because we defined the cost function in this manner. You may have seen the same gradient vector being defined in slightly different to what we have down here, and this has absolutely everything to do with the way that you define the cost function. For example, if instead of this definition here, we define a cost function in this manner, all that we have changed here is the order in which we do the difference. It's the same difference and the same square value essentially, but we have done our prediction minus the actual outcome. And if we were to carry out all the maths that we did previously, all that would be changed is simply the minus here would disappear, so we have this. And also, as you can tell, the error bit inside here changes the sign, so it becomes the minus version of this thing. So you may have seen this formula, but you might also have seen people defining the cost function in this manner here. And if you have defined this cost function, you essentially end up with the same thing as up here, but except we obviously have I'm just going to copy and paste. We obviously have a 2 over m there. And likewise, I've seen also people defining, instead of 1 over m, they have 1 over 2 here. And as you can probably tell, the end result is that you have 2 over 2 in the end here, which just becomes 1. In other words, this formula just becomes, you know, even simpler than it actually is, with just this this as your cost function. But it entirely depends on the way you define the cost function. All of these alternative definitions have the same exact outcome. In other words, they just measure the difference between your prediction line and your actual outcomes in a data sample and square it. But they have different factors at the start of the cost function. Maybe the error is defined in a minus way, in a negative way before the square. But they all do the same thing. It all achieves the same thing, which is finding the direction of the cost function relative to a particular choice of W. And you can apply all of these different end results to gradient descent and it would work just fine. Okay, I'm going to leave the video here, guys. Just one more thing, if you're actually interested in implementing this rule here, because you know we've derived the gradient descent, but we haven't actually talked about how to code it, and the code is actually very simple. I am going to be creating a post which will be linked on the description, and we're going to implement this with Python, NumPy, and Pandas, and it would sort of look like something like this here. So we've got a data set that I downloaded from a random website, Kaggle, and we've got some data, and we're going to fit a line to it using gradient descent. Okay, and the code is very tiny, it's very easy to understand. And now you should hopefully know all the maths behind it, so it should be even easier for you to understand all of this. I hope that you enjoyed this video. I hope that it taught you all the maths behind this commonly used algorithm. And if you did enjoy it, please drop a like and subscribe to the channel, and also visit my website. And that is it. Thank you. Bye bye.